As a matter of fact, we now have an event, and I'm going to skip questions if you don't mind, because we have something which will take us about 6.5 minutes, but it's something which for most of you is going to be a bit of a surprise. The first thing I want to say is that the Vice-Chancellor was very sorry not to be here. He's a deep addict of computation, rather more of a hardware person than a software person, but he really would have been here if he could be here. In the course of preparing for this, as you imagine, we have become acutely conscious that we are the guardians of a unique piece of scientific history. We have to make sure that this moves forward. As it happens, we're very lucky to have with us the new Pro-Vice-Chancellor, Regius Professor of History, and I would like to call on him to perform the next piece of what we might call virtual gymnastics, but before that, he's going to say a few words. Pro-Vice-Chancellor.
Well, we're here to celebrate an extraordinarily auspicious anniversary, a first for Cambridge, of which I think we should all be deeply proud. And I don't need to remind anyone here that what we're commemorating is the first calculation performed. I hate acronyms, being a humanist, so I will call it the Electronic Delay Storage Automatic Calculator, built by Professor Maurice Wilkes and his team. And I think we ought also, as it were formally, to celebrate the splendid fact that to explain how it all did get going, and with a really wonderful combination of erudition and wit, and the cosmic and the domestic, we have had Professor Wilkes himself on hand. Thank you very much indeed. I feel deeply honored to be invited to take part in a ceremony which in 3 minutes' time will associate itself with these celebrations, although you might think it a little bit ironic, since I'm a mere historian, that I have been invited, although it's true, of course, that I am also impersonating the Vice-Chancellor, which I do quite a bit. But as Robin very kindly pointed out in his opening remarks, in another way, it's perhaps appropriate that you should have an historian here. I mean, for one thing, historians love anniversaries. In fact, without them, there wouldn't really be the possibility of tenure. But for another, this is quite an anniversary, and I want to make sure I speak precisely here. So I want to quote the words of, I think, the really superb brochure which has been given to you in connection with this event, in which I spent yesterday evening reading. We're commemorating EDSAC's computation of squares of 0 to 99, the first logged program of the first complete and fully operational regular electronic digital stored program computer in the world. Applaud, please. But there is another reason why it's not inappropriate that a humanist should stand before you, which is that there's something else about this occasion which brings together scientists and humanists alike, which is that this great engineering development led to the start of the university's computer services. And when in May of 1937, the then mathematics laboratory was chartered by the university, one of its designated tasks was to supply computer facilities to the university at large. And by now there is surely no one, humanist or scientist, who has worked in this university for any length of time, who has failed to benefit from the, I've always found, extremely user-friendly services which became known after 1970 as those of the computer laboratory. Indeed, I sent them a cheque for £30 this morning for a new terminal which I have to have in connection with this onerous new task the university has placed upon me. I think it's going to be my own £30, by the way, but let's hope something might happen. Anyway, So a further reason for celebration today is the fact that Professor Wilkes's pioneering science so quickly made available, and for the first time, computer facilities to persons other than those concerned with the construction and running of the machines themselves. Now, it has been wonderful to hear about those great pioneering days, and that is matter of celebration enough in itself. But as has already been pointed out by Robin Milner, we can't fail to note that that great moment in 1949 was itself the start of something so great that it must surely have been unimaginable at the time, and that is the utter transformation of the world of all of us present by computers. As Robin said, what was invented was not merely a new human practice, but really something that deserves, and I think especially humanists feel this, to be called a miracle. So let me end these remarks by returning to that miraculous moment, which was the 6th of May in 1949. And I want now to tell you to a plaque which will now commemorate that great moment in lapidary form. And the moment, I think you'll agree, was passed by with a rather grand gesture of disdain by our very, very eminent speaker, and so I am going to emphasize it, or at least I'm going to do so if I can now master a piece of technology. Because if I can, a notional curtain, which in fact you see before you, a rumple-free curtain, will or ought to roll aside so that you will be able to see a virtual version of an actual plaque which will celebrate this very great Cambridge achievement. And so, in a moment, here goes, but not before I say, if I may, in the name of our university, to all who were involved in this spectacular achievement, and it's been moving to hear how many have been able to speak of it 50 years later today, may I congratulate, and in the name of the university, thank you all very much. And now, here comes the high technological moment. Now, since I suspect that very few of you are humanists, I'm going to read it to you. Near here, I like that precision, by the way. In the mathematical laboratory, on 6th of May, 1949, the EDSAC computer, built by Maurice Wilkes and his team, performed its first calculation. Thank you very much.
Thank you very much, Pro Vice-Chancellor. That was a wonderful humanization of our activity. At this moment, there's somebody with a hammer and a screwdriver and whatever else is needed doing that in an actual manner outside. And what you have to do in the tea break, which will come after the next talk, is to go out and, by seeing which direction people are moving in, you will actually find what near here means. As a matter of fact, I mean, near here, you might think, is not something which is a very portable phrase. If you had to walk 150 yards, you might ask whether it was true in this room or whether it was true wherever you got to. As a matter of fact, it's neatly arranged to be true in both the places. So that's all right. But if this talk gets shown somewhere else, then it won't work. That's the kind of thing computer scientists have to face these days. However, it's time now to move on to our next speaker. I'm very privileged to be able to introduce David Wheeler, who was actually the author not only of probably the first PhD in computer science, but of course, logically the author of what must have been the first program, not so much the table of squares as the program that read that program in, which of course was the initial orders. David has become an institution in the computer laboratory with interests ranging widely, even as far as computer security, which of course is a very new topic, one of the new topics that keep on arising in our subject. However, today we're very privileged to hear him talk about the EDSAC 2. David Wheeler.
There was a slight thing there about EDSAC 1 starting. It started there, way just behind that corner. The building was knocked down and this was put up, but that's where it started, so near here is fairly accurate. However, let me move on to EDSAC 2. EDSAC 2 was started by Morris, I suppose, in 1951 when he received a grant. I suppose he'd applied for it before, a grant of $2,000 from the Nuffield Foundation, and work began on conceiving and constructing a new computer to replace the EDSAC. In the early years, there were some decisions which, well, they look straightforward now, but they had the ring of newness about them at the time. The machine was made bits sliced. It had 40 bits in a word length, which seemed about right at the time. It could work as slowly as you like. It wasn't dynamic. It had a clock to run it, and a lot of those early decisions were taken place. And this actually amounts to about, I think, 2/3 to 3/4 of the machine. There were a few problems which arose in the early days. One of them was alluded by Morris earlier, what to do about the store. By then there was the Williams store, but that required really careful engineering, and we weren't too happy about it. Mercury delay lines were too slow, but fortunately in the States, ferrite cores suddenly became available, or at MIT they became available, and these were used for the store for the EDSAC 2. They'd not been made in England before, and Mullard's made them. And you didn't buy a store in those days, you made it. So you made it of little ferrite objects, you wired them, assembled them, grouped them together, and you made your own store. We were slightly uncertain, but let me just try a few diagrams which might help you with the principle. The old people will of course know all this, but some of the more modern people will have forgotten about core stores. But they did exist for about 30 years as the main stores of nearly all computers. How did they work? Well, you had a little ring of mud called a ferrite. It had some iron in it, and you could magnetize it one way or the other way. And it had some nonlinear properties like a permanent magnet. You could permanently magnetize it one way by applying a large magnetizing force. You could reverse the magnetization. Oh, sorry, I went the wrong way. You could reverse the magnetization, you could reverse the magnetization. And so it could memorize things. All you had to do was to put an extra wire through. And if it was magnetized one way and you reversed it, you got a large signal. Otherwise, you got a small signal. Oh, ideal. It had an extra property, which was the reason for its success. The extra property was that when it was magnetized, you could jiggle it by half a magnetizing force and it didn't switch. If you twiddled it by one magnetizing force in the right direction, it did switch. And this nonlinearity made it very, very useful. I used to tell my students, the one property of magnetic cores which is delightful is you could test them before you wired them up, and then they lasted forever. Why did they last forever? Well, if you go to any ancient civilization, the only thing which endures are the ceramics, crockery, and this was a ceramic. So unlike valves, which died after about 3,000 or 4,000 hours, or resistors which changed their characteristics with time, these were stable and nice and pleasant. The other part of the design was, of course, that we had to use valves, and these faded. But with the EDSAC 1, we'd learnt about marginal checking, which aimed to discover failing components before they made a fault rather than after a fault. Or should I say, they made a fault during the engineer's time rather than during the programmer's time. And what was the engineer's time? That was about 10 to 20% of the total time. There was a lot of maintenance. Oil, mechanical things, tape readers, fading components, and so on. However, let me proceed a little further with our magnetic objects. We made them into a store, and the store essentially consisted of frames of 64 by 41 little 2mm ferrite rings through which we wove 2 or 3 wires, and it was possible to read the content of a single core without affecting the others using the 2-to-1 property, and this made the basis of a store. The reason for its success was not quite that. The reason for its success was the electronics only went along the edges, and so it required far less electronics than just using one core and switching it back and forth. An array of them was very useful. While I'm on the subject, this is the last rather horrible diagram. There was a control matrix for EDSAC 2, which was the heart of the machine. It used microprogramming as advocated by Maurice Wilks, and it was implemented by some large cores, 13 millimeters, on which there were many windings. And the principle was roughly the same, except it used a slightly different characteristic. Roughly, if you had 2 windings on, it would switch, and only 1 winding on, it wouldn't. And so if you make a matrix of them, you can arrange to switch 1. And along the edges, you had drivers and flip-flops and garbage. And basically, the switching mechanism worked by 2 to switch it and 2 to drive the next row and column. And thus it switched gently through a system. And occasionally, one had a conditional sets in which you switch 1 of 2 cores, depending possibly on, the sign of the accumulator or modifier register or something. And there was about 1,000 of these all connected together. 120 of them were used as a function decoder. And some of them had a rather larger number of windings than I show here. In fact, if we look at, I think I've got the wrong one. This shows Sid Barton and Norman Unwin on the back of the memory planes. You can see the wiring was quite intricate. In fact, the wiring was something which one could do in-house. One soldered and did it. Another diagram is this one, which is Norman Unwin, with the back of the control matrix. I don't know if you can see the intricacy of the wiring. I shouldn't think you could, but it does show a little how the information was wired into the system. A slightly better picture of the other side of the control matrix was this. There were driver units and so on. For those engineers present and anybody else, this was the back of the machine. Well, back isn't the right word. It was a U-shaped machine, and the engineers were put in the middle. And they could see the indicators of all the single flip-flops of every register in the arithmetic unit and control. And there was a little switchboard, so they maintained the machine from the back. There are some examples of the switching units, the units of which the machine was made. This shows one down here, and this is the front of the machine with tailored doors and all this. But behind them, there were these enormous plug-in units. This gives you, I think, by far the best idea of the machine. There were lots of plug-in units. In fact, the arithmetic unit had 41 identical units. The control unit had 11 identical units. The store was controlled by 20 sets, and then there were miscellaneous ones for the control matrix and so on. So there weren't all that many. I better not quote the exact number. I think it was somewhere about 12 or 13 different types, of which nearly all of the work was in the first three. So this was how you repaired the machine. You unplugged something and you plugged it in. If you notice carefully, there was an enormous screw which went right through and was twisted in order to lock into a socket at the far end. And it was twisted, and quite enormous force was applied. Contacts were very unreliable in those days, and you had to take precautions. Right, well, what happened after that? Well, with the ideas of the control matrix and all the other stuff, there was then the little task of what should we put in them? What order code should we have? We could choose it. In fact, I think we're probably at the most favorable position that anyone has ever been. We had some experience with the EDSAC 1. We believed, possibly falsely, we knew what our users wanted. We had no compatibility constraints with anybody else. And we could choose to put in facilities which we thought important. And we tried to do this. There were a large number of innovations this way. After the mechanical design of the main part, there's a question of how you should fill these up. Should you use floating point? Yes. Should you use fixed point? Yes. That may have been a mistake. It wasn't used very much. Should you write an intricate assembly routine, or should you provide a few fixed point routines and so on? Talking of fixed point and routines, ferrite cores I've described actually two uses, or possibly three so far. They actually were used in quite a number of different devices. And one of the most important was the fixed store, or the private store, where instead of a single little core just storing one bit, it stored 4 bits, although you couldn't change them. And the extra 4 bits were inserted by inserting one of 3 wires, up to 3 wires through each individual core. And this made a little fixed store, which couldn't be altered, which had, I think, 768 words. Which is not very much by present-day standards. And we had the control matrix or microprogram with another 1,000 steps. So we had to put these things in. So that was a kind of a third use. This was very economical, actually. The fixed store used the same amplifiers as the main store, the same drivers, and so it just slipped in with no extra valves, which were not so reliable as the ferrites themselves. So after that, there was a question of what to put in, and we decided to put as much in as possible. And make it easy to use for the users. And so there were many facilities some of which are quite quaint to you. We actually arranged that you could actually print out a program before you ran it in a machine. You couldn't do that on EDSAC 1. You wrote it out and punched it, but you couldn't print it. On EDSAC 2 you could. Some people liked that very much indeed. We hadn't reached the advanced stage of allowing comments in a program, but to print a program you took a teleprinter and this printed 6.5 characters per second. So it took some of your time if you wanted to print anything really elaborate. So possibly it was quite sensible. Well, we shoveled facilities in, and I can't list them now, but they're the obvious ones like sines, cosines, logarithms, arctangents, assembly routines, printing routines, routines to control magnetic tape, fast binary input, integration of differential equations and matrix division and so on. And these were just part of the autocode built in. And of course, you have to describe the autocode to people. And so Morris, as for EDSAC 1, had a little book prepared. This book, of which this is the front cover, this should be the front cover. Does that show up? Contained all the instructions, the content of the wide store, how to do printing, how to control the layout of printing, and roughly everything that a programmer needed. There was about 60 pages. It also told him how to program as well, and that was more or less the complete Bible. There's a fair number of people probably here who were able to use the EDSAC merely after reading the booklet. It's slightly better than some help schemes of today, but we didn't have quite such a problem with too much data. Well, this was the book. To read the book, you had to understand the structure of the machine, which I didn't go into before. There was an accumulator. It was a double length as far as fixed point was concerned. It had two 11-bit modifier or B registers, and it had a little store of 1,000 registers and a hidden store of 768 words plus 64 for doing things behind your back, which was very useful. In addition to that, there were various peripherals. It started out with one tape reader and one tape punch. Later there were two tape readers, two punches, 4 magnetic tape decks, double deckers, as described by Morris. And these were controlled, and almost everything was controlled from the control matrix. Magnetic tape was handled from the control matrix. So certainly finally, if you wanted to transfer 1,000's a big number, 538 words into the store, you said transfer 508 words starting from here on the tape into the store, and it did it. And the tape system was peculiar. Well, should we say more advanced than the other systems of the time. It had lots of little blocks of 50 words on the tape. And when you specified a transfer, if you happened to use half a block, it didn't really matter. You just went on to the next block for the next transfer. This meant that you could access anywhere on the tape as if it were a store, as well as just shunting data around. Anyway, you really had to kind of understand that if you wanted to learn to program the machine. The middle pages of the programming book happen to be that. I don't suppose you can read anything, but it gives you it gives you a flavor of the book. Now, most people, of course, don't like carrying even small books around, and so there was a summary sheet. It doesn't quite fit foolscap. A4 hadn't been invented. It was a foolscap sheet printed on one side and had the order code and print instructions and tape code instructions. You can see it's slightly better on that, which is just the top half of the summary sheet. You'll notice possibly that the order code did not use mnemonic coding. Many people get upset by this, or did, mostly non-users, mind you. Instead of having A for add and S for subtract, you soon find you've run out of A's because you've got fixed point, floating point, modifier additions, and so on. There's just too many of them. So instead, they were organized systematically in a decimal code. And you can see, if you study it carefully, it's supposed to be systematic. The noughts indicate clear loading, ones indicate clear subtract, 4 is multiplication, 5 is division, and these hold for fixed and floating and so on. So that's what the programmers had to contend with, and on the whole, they seemed to enjoy it quite well. How did they approach the machine? Well, that was an early control desk. That's the user view of the machine, or programmer's view. There was a control panel, of which there's only about 3 useful switches. These 40 switches allowed people to specify decimal numbers for strange things like printing out a portion of the store. You can see there's a punch and a tape reader, a very early version of the fast tape reader. And this is essentially how the machine was used. Perhaps a better impression is of how the machine was used is this rather better indication. The operating system was a queue. The help system were the people behind you in the queue, and usually the advice was good. The way that you ran a program was you wrote out your program, you then went to another room and you punched on a keyboard perforator a little paper tape. You brought your paper tape to one end of the queue. When you were allowed, you reached this end, you dropped it in the tape reader, the machine read the paper tape, it ran your program, it punched a tape to give you the results, and then you took away the results elsewhere to consider. In this way, one machine could deal simultaneously, roughly, with quite a large number of people. When the queue was not active, there were operators to load tapes. I should mention a favorite of the programmers of the time. One of the things we built in was a so-called report. Nowadays, you'd call it part of the operating system. Whenever the machine discovered that you were using a number form that you shouldn't, or using a non-existent order, or trying to find the square root of a negative number, or some such thing as that, it stopped immediately and printed out the content of the accumulator, where you were, the order, and the contents of the modifier registers, stopped the machine, and so you moved elsewhere to debug your program. This was an efficient operating system type implementation. You never stayed, should I say never? You didn't stay at the control console and try and debug your program there. There were no lights on the programmer's console. They were all on the engineers behind the machine. So, all right, you printed out the results in decimal, which is rather more understandable, and went away to join the queue again, presumably. The machine lasted for quite some time, and it evolved. It started out, as I said, roughly with 2 tape punches, but there were many things which happened. We had a graphical output, which was a cathode ray tube, which could show a point or a short line. Actually, it was the fastest way of getting data from the machine. except that the film had to be taken away, developed and printed, and so there was quite a long interval before you actually got results. So most people preferred to print them at 6.5 characters a second, or were forced, or alternately were forced to. Other things which were added later, there was a remarkable high-speed punch from Creed, which could actually punch paper tape at 300 characters a second. It wasn't used possibly as much as it might be because of maintenance problems. Whenever it jammed, it had to be taken to pieces to unjam, and this took quite considerable effort. Eventually also a line printer was added of a crude ICT variety, which could print as many as 0 to 9, a point and a minus, nothing else. But it did print at 2 lines a second, which is considerably faster than nearly all other ways of printing. And by making a ferrite core buffer, you could actually use the printing routines which were already in the machine. So that was quite attractive. One day it almost produced a most remarkable document. It grabbed the hair of Van Neville and began chewing it, and the machine was stopped just in time. I leave it to your imagination what the result would have been. There was one rather nice device which was attached to the machine, which was another graphical device, which is the CalComp plotter. It had a pen which you could move up or down, right or left, on the paper or off the paper, at about 200 steps a second, and it was connected to the machine as a graphical output. I remember it particularly well because it was the only device which we ever attached to that machine or to some time in the future which worked according to its specification. It worked first time when we connected it, and there were no teething troubles. In fact, it survived a remarkable length of time because it was transferred to the Titan, and then transferred to the cap, and then transferred to the ring. And so it had quite a long life. Let me kind of finish by assessing more or less what the EDSAC 2 did. It had a very large number of users from all departments, and more or less trained the university, even more than EDSAC 1, on the uses of computers. It was fairly simple to use, and most people could use it from a variety of places. And the research students of that time became heads of departments in due course, and at least one felt they understood a little about computers and weren't repelled by the thought. So it influenced the usage of computers in Cambridge quite considerably. Well, among its other achievements, I guess, you can mention that in the course of its life, 2 of its users got Nobel Prizes for work which they wouldn't have done without the computer. The radio astronomers used it as part of the telescope because they sent little paper tapes along to convert the observations they got by a Fourier transform into representations of the sky. So, with that minor clarification, I will stop at that point.
We now proceed with the real story. I'm Peter Robinson, by the way. Despite appearances, I'm a youngster in the computer laboratory. I've only been here 25 years. And I've been trying to help Karen organize it. I think the belief was I wouldn't lose any hair worrying about it. Our first session this afternoon features the engineers of the laboratory. The lab photograph of 1949 shows 20 people, of whom 7, I guess, were employed as engineers working on designing and building the EDSAC. And the lab has always been a practical department. We've built things, and we've relied on our engineers to make things work and to keep them working. And well, they know the inside stories, which some of you will have heard, doubtless, before my time in the bun shop and in my time when the Cambridge Beer Festival appeared in the Corn Exchange, conveniently close to hand. Lengthy lunchtimes could be spent there discovering the truth about the department. And we thought that it would be important for the engineers to tell their side of the story. Those were lengthy lunchtimes, and we needed to distill it down into the 30 minutes available, so we've actually commissioned a videotape recording of the engineers, and so we're delighted now to present the world premiere of Behind the Green Door. Thank you.
The best time of my life, the most productive, the most interesting, without a doubt. It was the pinnacle of my working life, without question. It was magic. The laboratory in itself, the atmosphere, everything about the place to me was magic.
I thought it was a very interesting, a very exciting job to produce EDSAC, but I didn't think this, I mean, when you looked at a room full of about 3,000 valves, who the hell's going to use this sort of thing for a computer? It's nice to prove it can be done, but it's not going to catch on.
Talk about a rogues gallery.
The Green Door is the last remaining exhibit of the old building which we have in the lab. It was the only entrance into the department from the Corn Exchange Street, so it was used frequently.
I've always felt very proud to have been working at the maths lab. It was a job that I thoroughly enjoyed doing, and the staff and everybody were terrific to work with. And I just feel that computers have come on so much that I can't really relate it to that original equipment.
In those days, there was very, very little that you could buy off the peg. All of the stuff on EDSAC virtually was handmade, largely because it just wasn't available outside. It had to be developed on the spot. We had a design engineer and people who would do that side of it, and then it had to be made, and then it had to be made to work, and then it had to be kept working once you'd got it. So there was that sort of background to it. You could go out and buy components, bits and pieces, plugs, sockets and electronic components, but there were very, very few things, in fact virtually nothing in those days, put together and readily available for computers.
Well, there's been many changes and many technologies. I mean, the first machine was built with war surplus valves, large valves. EDSAC 2 was a miniature valve machine. We never did build a transistor machine. We should have done.
Built everything from scratch, especially EDSAC 1. Everything, I mean, you bought the aluminium if you could buy it, otherwise you scrounged it, and you actually built everything from scratch, yes. You had lathes, guillotines, drills, and everything was made by hand. And this continued on with EDSAC 2. EDSAC 2, in fact, was all homemade.
Well, originally the input to the computer was done by tape, and the tape was produced with punches, which is all well, mainly mechanical, and it was read by mechanical readers. And then they had comparators which compared one tape with another, and of course there was equipment to print these tapes out on a teleprinter.
I mean, we had to make things like tape readers and modify various telegraph equipment so that you could get information into the machine. I mean, in EDSAC, all of the stuff that went into the machine went in on telegraph tape.
All that early development on tape readers was done by partly Gordon and latterly by Herbert Norris.
When Gordon went upstairs, I took over one of the jobs that he was doing, which was developing a tape reader. The main aim was to get it to run faster. Originally it was working about 19 characters a second, and we got it up to 1,000 characters per second.
I was from the engineering labs, and that was where I first met the readers, because they were, after the first one, were produced at the engineering labs. And then I followed them here to help maintain them and build other equipment.
But if you take the case of the paper tape readers, the basic paper tape reader that was in use on EDSAC 2, which was designed and built here, would read tape at 1,000 characters per second, flat out. Woof. Well, I can remember when we had the PDP-7, which was the first digital machine here, they had their so-called wonderful tape recorder, which would maximum 700 characters.
Yes.
And it was extremely reliable, that 5-hole reader.
Yeah.
Its unreliability came from, I don't know whether it was Ferranti or Elliott's modification to make it 5, 7 or 9 hole.
Yes.
And that modification never worked as well as it should. But as a 5-hole, as it was originally designed, it was cracker.
Of course there were problems. I mean, Herbert designed the lens system and it got a curve on the back of the prism.
Yeah.
And he sort of picked a piece of tubing out of the store and said, oh, that looks about the right diameter. And carved up the perspex, filed up the front, and it worked well. Then Elliott took it over, and of course they said, we can make a better system than that. And they had lenses by the dozen to try and get this extra sensing of the outside characters. And eventually they came back to a perspex lens cut up with a piece of perspex, with a piece of tubing.
Each morning when we came in, we would run a fair number of tests through the machine to check the various functions of it. The machine, as you can see from the photographs behind me, was made up of a collection of units, which we used to call chassis. And in the event of one of these failing, it will be taken out, changed for another one. And when you'd actually finished working on the machine itself, then there was that chassis to be investigated in a sort of small replica of EDSAC, as it were, somewhere else. And the fault narrowed down to whatever components were causing that fault.
It was a challenge, I think. I mean, to some extent, every day would present a challenge, one form or another. And you had, well, you got to use your ingenuity and your brain a little bit. And if your ingenuity and brain wasn't good enough, then you could go to Norman Unwind, who would tell you to go away politely, and then an hour or so later you'd find the answer written on a little piece of paper somewhere and say, try this.
Norman was a great individualist. He was a real electronics engineer, and occasionally used to mutter about the amateurs and so on, and be a bit gruff and a bit grumpy, but that was largely a surface appearance. He was a very good person to work with, and a great fount of knowledge, certainly.
We had a chief engineer then. Well, it wasn't his title, actually. That title didn't exist. The senior bloke was a Scot, Bill Rennick. You may have heard of him, but someone else will mention it if I don't. And he was, well, he'd got a beautiful Scottish accent, and I think he was a product of Glasgow University. He was a fine engineer and a fine man.
One of the other people was Sid Barton, who was in charge of the team, and he was a very pleasant character to get on with. But the main thing about Sid was that he'd got the most fantastic memory I have ever encountered. You could show Sid this setup in here today, and he could come in tomorrow and set it up for you. He'd got an almost perfect recall of EDSAC 1, the computer before EDSAC 2, and any details which Sid encountered sort of went into his memory, were stored there, and they were there forever.
Fridays was very good because Friday was payday, and the lab had a buzzer system, a coded buzzer system, I remember, and when a certain code went, everybody shot down to Professor Wilkes' office to collect their weekly wage.
He was a mixture. You had to be very careful, because he was the sort of person who could change like that. He would be quite happily discussing something with you, and you'd make the wrong remark, and to put it mildly, he would turn off instantly. But on the other hand, if you came in to do the early morning run-up of the machine from 8 o'clock onwards, at any time between 8 and 9, he would appear. He would come into the computer room, he would ask you how it was going and any problems, and how you're getting on and so on, and in that respect he was very good indeed.
Two things that stand out in my mind. One was that he said, the wonderful thing about seeing engineers with the feet up, it means the machine's working. So that was one of his statements. And the other one was, when you'd found a fault, he'd say, right, across to the bun shop for a pint. So the bun shop was a pub just across the road. So we'd all troop out of the green door and go across, and MV would stand us all a pint of beer because we'd found the fault, the machine was up and running.
The very early day when I started, you had to actually go into Morris's office and shake hands with him and thank you very much. Then he very quickly handed it over to his secretary to do the same thing. But yes, you still had to go down in person and sign for your weekly salary.
And in those days, we had to go personally and collect our pay from him in his office. And he would ask you, what have you done for us this week, Kimpton? And you'd put your hand out and he'd hang on to the pay sheet. You was one side of the desk and he was the other. And eventually he let go. And there was all of £2.12 and sixpence in it.
My take-home pay when I started was £12 a week. And out of that I remember paying £3 10 shillings for my bedsitter along Cheston Road. That was a week. So I still had a good £7–8 to play with, which was luxury in those days.
That computer, as the whole of the computing services today, was open to use by anyone in the university. And the thing was that at the time I came in 1959, it was the only computer in Cambridge. So you were bound to feel that you were stuck out on the top of things like that.
Well, the users were obviously running all sorts of things. They'd come in from all the departments, astronomy and mathematical departments and things like that. I remember one program that used to run on EDSAC 2, and it was used as the standby program if nobody else was there. And that was Dr. Miller's program to locate prime numbers. And this program would run forever. You just let it run on and on and on, and then when somebody came in to use it, you would just stop it.
Senior academics in the early days, they were the main users. And as time went on, more and more people, and then students started to have projects. But in the beginning, it was mainly senior academics who thought that computing would help their research.
The usual problems arose when they made, quote, a little change somewhere. And yes, I've only made this little change, but in practice it fouled everything up for miles around, and if they took that little change out, the odds were it would run, and then they would have to go and scratch their heads a lot more about it.
It was a different world, a quite different world, surrounded by different ideas, different minds, different people. And I loved it from the first day. I thought it was an incredible place to work. There was a good bunch of people to work with, as Peter said, the odd eccentric, but nonetheless, even the eccentrics were actually underneath very nice people. I do think that the director, M.V. Wilkes, I think he had a very good idea of where it could go. I mean, he's credited with saying once that computing will take off when memory becomes small, cheap, and easily available. And I think it's probably true. I mean, EDSAC had one kilobyte of memory. There's 1K memory, 1024 locations. And there was a pair of Ampex memories added later, which gave it another 18K, all told. I think that's correct. I think it was about 18K. And I mean, that was unbelievable. But now, what you get on one chip. And that memory, that 1K of memory was bigger than, well, it was about 4 foot long and a foot high and a foot wide, core memory.
The machines themselves would take up a whole room to start with, and it would be quite a reasonable sized room, not a very small room. And that would only be the actual main machine. There would be an area where the users would come with their programs to run, and that would be a table with a tape reader on, and there would perhaps be a line printer in the later days which they could actually refer to. And of course, as things progressed, magnetic tape decks were added, first of all to EDSAC 1 and then to EDSAC 2, and then the number of tape decks as you got to Titan would be increased, again to cope with the load. So gradually the machine would take up more and more space, really, because it would expand into either more of its own room or into another room completely.
It became a symbol with its mathematical name on it. And as you say, it was the most unimpressive entrance into the lab. You used to open the green door, walk past the dustbins and up the stairs. And, but it was the main entrance. Very unimpressive.
That was the front door into Corn Exchange Street, and that was about the one bit of the building that was saved from the demolishers, apart from various odd second-hand electrical items which disappeared in all directions when the demolition time came. So that was the front door. That was the way in and out of the building, and that was the biggest, most tangible bit of it that was left after the dust and debris had cleared.
The old mathematical laboratory was intriguing because it was the old anatomy department which they'd taken over, and I was told to come down Corn Exchange Street and look for a green door halfway down Corn Exchange Street, and to come through that door and go up the stairs to the first floor to the reception. And I did this, met Neil Wiseman, who was at that time the chief engineer here, and came into a world which I'd not really appreciated could exist at that time, and the friendship and the small unit, the way they were sort of became a team was amazing, really. It was a different setup completely to Jodrell Bank. Jodrell Bank was all big and open spaces and so forth. Here at the mathematical laboratory, we were all one tight-knit community of about 40 people, and everybody knew everybody else. And the only person that we didn't call by the Christian name was Professor Wilkes, who we called Sir. I always remember that.
If I speak as an engineer, I say it is not the interesting world that it was then. Because you were, that time, you're in the nitty-gritties of it all. And I think almost any computer engineer worth his salt who was around in those days would say today, you don't find faults and you don't repair things, you replace things. It's a bit like the car industry, you know. Windscreen wiper goes, okay, buy a new car. It's a little bit that way now. So some of that interest has gone from an engineering point of view.
Mainly it was the people we worked with. We were sort of included, whereas having been brought up in a factory, one was just a number. But here one was treated as a member of the staff and consulted. And I don't think there was anybody here that I can remember not getting along with.
I remember sitting cross-legged behind the back of EDSAC 2 with Bill Rennick discussing, I don't know, back warring schedules or something, and suddenly there was this voice saying, "Fire! Fire!" And Bill said, "Who the bloody hell's that?" And it was poor old Gordon. He'd gone in the tape preparation room, and one of the duplicators had caught fire. And he opened the door and he staggered out.
Again.
And somebody grabbed an extinguisher and put the thing out.
No, I think you've got the wrong character on that one. I can't think of that. I don't think I ever set fire to the EDSAC.
Well, Gordon Stevens, I came across Gordon very early on when I joined the lab because he was the principal assistant, and he was responsible for giving me my membership card to the assistants club. So I remember either the first week, I think it was, one day this man wandered into the little office I was in and said, "Here's your membership card," and popped it on the desk, and "Can you sign this?" and "Here's your contract of employment," and so forth. And then off he went. And I said to the person I worked with, who was that? I think he forgot to introduce himself. But then got to know him quite well, of course.
I think there's a lot of nostalgia about it, but personally, I must admit, If it had been my green door, it would have finished up as firewood by now, but still, there we are.
Yes, I think they thought there was something here that was going to go well. I don't think they could ever have envisaged what it would have been like in 50 years' time, but I think, yes, they knew where they were going.
Engineers, Mick Taylor, Roy Bailey, Herbert Norris, Ken Fox,